So backpropagation algorithm. So let's say this is our neural network. It's a multi-layer perceptron where we have input layer. There are these two hidden layers, layer 1 and layer 2, and this is output layer. So we have this data set in the form xi comma yi. So this xi has three features in our case, xi1, xi2 and xi3. So there are n data points, x1, x2 up to xn, and each data point has three features, x11, x12, x13. So this data point also has three features, x21, x22 and x23. So what we are doing is we are giving one data point, this x1, that means these three features. One data point means these three features of that particular data point as input at a time. At one time we are giving this one data point as input to this neural network. So let's say we are giving this ith data point as input. So three features of this ith data point are xi1, xi2 and xi3. So what happens here? So these inputs are sent in the forward direction. So this first feature gets multiplied with this weight W111 and comes here in this neuron. The second feature gets multiplied with this weight on this edge W121 weight. So this multiplied with this and it comes here. So this feature gets multiplied with this weight and it comes here. And what happens here in this neuron? In this neuron, the sum of these multiplications is carried out. So we have a sum here. If I write a sum symbol here, so this is nothing but sum of these multiplications. So I have xi1 w111 plus this is xi2, this is xi2 into w121 plus I have xi3 into w131. So these multiplications are summed in this neuron, and on that sum we apply this function called as activation function. So the function here is f11, right? And the result of applying this activation function on this sum is nothing but this output. So O11, if I write O11 is equal to applying this function on this sum and that is nothing but output of this neuron. And the same thing happens here. So this input gets multiplied with this weight and comes here in this neuron. So this input gets multiplied with the weight on this edge and comes here, and this input gets multiplied with the weight on this edge and comes here, and this on this sum again we apply this f12 and the result of that is f21 again. So this f11 gets multiplied with this w211 and comes here in this neuron. So we have here O11 into W211. So this O11 gets multiplied with this W211 plus this O12 gets multiplied with this weight here. Weight here is, the weight is W2, it's going in the layer 2, W2, and from neuron 2 to neuron 1. So W2 to 1 plus I have this output here. This output is nothing but O13 and this weight is nothing but W. This weight is going in layer 2, W2, and it's coming from neuron 3 and going to neuron 1. So O13 into W231, and on that on that sum we apply this function f21 and we get the output O21, right? O21 is f21 of this sorry. So that's how we get the outputs of these neurons, and these outputs propagate in the forward direction, and finally we get the output of this output layer neuron. That output is called as O31, or it is also called as yi hat, and this yi hat is the predicted output for this input xi, or this is the predicted class label for this input xi, right? The actual class label is yi, the predicted is yi hat. So we compute the loss for this xi. So the loss for this input is predict here we are considering the squared loss, or it may be any loss, right? But the loss is the loss means how different is this predicted output from this actual output, right? So we calculate this loss, right? And then we update the weights, right? And how do we update the weights? By using the formula W new is equal to W old minus eta times the derivative of loss, partial derivative of the loss with respect to W old. That means if you want to update the weight W, that means if you want to get new weight, so new weight is equal to old weight minus eta times derivative of loss with respect to old weight. For example, if I want to update this weight W311, so I write here W311 is equal to W311 new W311 we want to get. So W311 old minus eta times derivative of loss with respect to W311 old. Right? So that means whatever weight I want to update, I need to calculate the derivative of loss with respect to that weight, and by using this formula I can update the weights. This eta is the learning rate here. So now how do we update these weights? Of course, while updating these weights and calculating the derivatives, we use chain rule and memoization, which we discussed in the previous videos. Right? So we rely heavily on chain rule and memoization. So chain rule means in order to compute the derivative of loss with respect to this, I compute the derivative of loss with respect to O31 and derivative of O31 with respect to W311. So that means if I write in short here, W derivative of loss with respect to W311 is equal to derivative of loss with respect to O31 and derivative of O31 with respect to W311. So this is chain rule, right? So we rely heavily on chain rule and memoization. Memoization means we compute the derivative once. That means if I compute this derivative, I will remember it. I'll store it in the memory, and later if I require it, I'll use the this. That means if I coming across again the same derivative later, I will use the result which we already computed. So that is called as memoization, which we discussed in detail in the previous video. Okay. So now how do we update this weight? Now while updating this weight, we update the weights in this layer first, right? And then the weights in this layer, and then the weights in this layer. So we go in the backward direction while updating the weights. That's why this name backpropagation. So while updating the weights, we go in the backward direction. That means we update the weights in the last layer first, then this layer, and then finally in the first layer. Right? So that's why it is backpropagation. It's called as backpropagation algorithm. Okay. So if I summarize now, or if I write the backpropagation algorithm clearly, it is like this. The first step is initialize weights randomly. First time you will have to initialize the weights randomly. Then what you do, send one data point, let's say xi, as input to the network, to the neural network, of course. Then what happens? Calculate the weight, the sum at each neuron, and pass that sum to the activation function, and then the activation function, the result of activation function will be the output of that neuron. Calculate the output of each neuron for 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 the given input. and finally and finally we get the predicted output, that is y I hat. So we sent one data point xi as input to the neural network, and then we, for that input, we calculated the output of each neuron for the given input, and finally we get the predicted output y I hat. So this is called as feed forward step, feed forward step, because the input is floating through the neural network in the forward direction, right? And then step number 4 is calculate the loss. Calculate the loss. Right? After calculating the loss, we update weights, update, calculate the loss for that particular data point xi, so that we are calling this loss as li. Right? Li. This loss is only for that particular data point xi. So then update the weights in the backward direction. So after updating the weights in the backward direction, and till how in the backward direction, so how many times we will update these weights till the convergence. Till the convergence means till the point when old weight and new weight are very similar. That means there is no difference in the old weight and new weight. That means there are no more updates, right? The weights are not getting updated. Till that point we'll update the weights. So these are step 2 to 5. Now we did this step for input xi, right? So we'll repeat these steps. We'll repeat these steps for repeat these steps. Repeat steps 2 to 5 for all the data points. That means we'll repeat these steps for all the xn data points. There are xn data points in our data set, x1 to xn. So we'll repeat these steps for all the data points. That means we'll send all the inputs through the neural network. So when the neural network sees all the inputs from x1 to xn, and when we repeat these steps for all these inputs, so this is called as epoch. When the neural network sees all the inputs, right? This is called as one epoch. Send x1 do this, right? Then send x2 do this, send x3 do this, right? So when we send all the data points and repeat these steps for those all data points, this is called as one epoch. So then finally step 6 is repeat these epochs. Repeat epochs. So this is the backpropagation algorithm, right? So if I summarize the backpropagation algorithm one more time, it is initialize weights randomly. The second step is epoch. In epoch, send xi as input, calculate loss, update weights in the backward direction. Backward direction means starting from last layer to first layer, and then repeat these steps for all data points. So this is one epoch. Now while updating the weights, we need to calculate the derivatives. and calculating this derivative will require chain rule and memoization. Right? These two are important things for calculating derivatives, and then only we'll be able to update the weights. And step 3 is repeat epochs. Right? So this is the backpropagation algorithm in brief. Okay. Now the important point to note is, the the function, the this function, this activation function, these activation functions must be easily differentiable. This activation function, these activation functions which are there in the neurons, these must be easily differentiable, right? Why? Because we are calculating these derivatives, right? So these derivatives, so derivative of O31 with respect to W31. So we are calculating derivatives. Now, though we are calculating derivatives of output, these output are coming from this activation functions only. That means ultimately we are calculating the derivatives of this activation function. So these activation functions must be differentiable. If they are not differentiable, this backpropagation algorithm will not work because we'll not be able to compute the derivatives. So these activation functions must be easily differentiable. That's the important point, right? So the other thing which I want to discuss is, let's say we said that we will pass one data point xi at a time as input, right? So this algorithm where we are passing one data point at a time as input is called as SGD, stochastic gradient descent, right? Now when I pass few, few, like let's say I pass x1, x2, x3 or x4, that means, I'm passing a bunch of data points as input, right? So here I pass only one data point at a time. At a time now I'm passing four data points, let's say. So what I'm doing is I'm passing a batch of data points as input to the neural network. So that's why this is called as mini batch SGD. When I'm passing a batch of data points, this is called as mini batch SGD. And when I pass all the data points at a time, all the data points from x1, x2 up to xn, I'm passing these all at a time as input to the neural network. This is called as standard gradient descent algorithm. Right? So I can use either SGD, mini batch SGD, or the standard gradient descent algorithm. Okay? Great. So that's it for this video, backpropagation algorithm. So we'll meet in the next video.